Last time we left off in the middle of chapter 1, section 5, and we were talking about this idea of limits that are involving infinities. And the last part that we had looked at left us here at Theorem 5.1 and Theorem 5.2. Theorem 5.1 actually has a function that looks similar to the one that we worked with the very first last time. This function right over here that was 1 over x, and we had this graph. But if you'll notice, the difference in this theorem is actually that we don't have 1 over x. We have a 1 over x to a power t. So this function actually resembles the function we were working at some of the time, but it does have the same limit as long as the t value is greater than 0. So any value greater than 0, even if it were like a 1/2 or a 0.1 or something like that, we're going to have these features. Now, if in fact we are talking about negative infinity that we're approaching, we do have to assume that the t value has a denominator that is odd. Otherwise, like imagine, if you will, that t were equal to 1/2. If t were equal to 1/2, then we would have 1 over x to the 1/2, which is equivalent to 1 over the square root of x. And if we were dealing with that, we wouldn't be able to have negative values underneath the square root. So the way that this is sort of dealt with in this function is we're saying that if we're talking about values that go to the negative infinity, then this denominator down here where I previously had a 2 needs to be an odd number, because then we'll actually have the ability to put in a negative value in that denominator and it would work. So any of those that have that feature have a limit that also approaches 0 as we go to the left or to the right forever. And if you take a look back at this function over here, you can see that it follows that rule. So if we go to the right forever, that is if our x values are approaching infinity, then our y values approach 0, or our limit is 0. And if our x values approach negative infinity, then our y value also approaches 0. And there's nothing particularly special about it being 1 over x, because any 1 over x to the t power with the conditions we mentioned before would have that same limit as we went to positive or negative infinity. The other theorem that we see on this page, Theorem 5.2, says that if we have a polynomial and we're looking at the limit as we go to infinity, that this leading coefficient actually tells us what the limit of that will be. If the leading coefficient is positive, then the limit will be infinity, and if the leading coefficient is negative, the limit will be negative infinity. I'm just going to draw you a real quick graph of a very familiar function that sort of illustrates this feature. For instance, if I had y equal x cubed, roughly speaking, that graph looks something like this. And as I'm taking a look at that graph, if I'm looking at the limit as x approaches infinity, that means I would be moving to the right forever. And you can see that this limit value then, so this limit of this y value is x cubed. I'll put x cubed in here. As x goes to infinity is actually positive infinity. Now, if the function had said very simply, y equals negative x cubed, that is the coefficient that a sub n is negative, then the graph actually sort of flips upside down. That's what it visually looks like to us anyway, and it would look something like this. And then clearly as x goes to infinity, we would be moving downward, because moving to the right actually also makes us go down in this case. So as the x values increase, the y values decrease, and the limit as x approaches infinity of this graph of negative x cubed is actually negative infinity, just like it says back up here in this limit. And this works whether we have an odd degree or an even degree. There's nothing special about that. So whatever the leading coefficient is, the sign on that really tells us whether we approach positive or negative infinity. All right, so I'd like us to take a look at a few examples where we're determining the limit, and we're going to decide if they answer appropriately with a number, with infinity, negative infinity, or does not exist. And we're going to see a few different things happen. Now, taking a look at this one, what I want you to recognize at first, that this is a rational function. And when we were dealing with rational functions before, we talked about something called horizontal asymptotes. And when we were dealing with horizontal asymptotes, we said that when we had the degree on top and the degree on bottom the same, that the limit is actually y equals the ratio of the leading coefficients. So in this case, 2 over 4, or y equals 1/2. Now, the reason that's important is because what that tells us is that this graph, as we approach positive or negative infinity, actually approaches the line that is the horizontal asymptote. So in this case, I'll do this as my horizontal asymptote y equaled 1/2. We'll call this number 1. That out on the ends of the graph, right, over here and over here, we get close to that line that's the horizontal asymptote. So no matter whether it's coming at it like this, or maybe it's coming up like this, on the end, we still get close to that dotted red line, which is the horizontal asymptote. The reason that that's helpful and that that matters is because that's actually what the limit equals then. So we were looking at the right-hand side as the limit approaches infinity on the x values. Then our actual value of our function, I'll call this function f of x, so I don't have to rewrite it all again. So let's just call this f of x, would actually be equal to the same thing as the horizontal asymptote. And that really is what the crux of this particular section is about, is that horizontal asymptotes have this sort of interplay with limits that make them most of the time referring to the same quantity as we approach positive or negative infinity anyway. Let's take a look at another one. Now this one's a little bit different because it's got square roots involved. But I want you to think about what you know about that number 4 plus, or that value 4 plus. As x gets infinitely large, adding 4 to that value doesn't change it much, right? If you had $1 million or you had $1 million plus 4, it wouldn't be significantly different. So that 4 plus actually has very little effect, actually no effect on the limit, which means that while the functions are not the same, the limits are going to be the same if I were to simply ignore the 4 plus. Let me say that one more time. This function right here and this function right here, these are not equal. However, their limits, as we go to positive infinity, are equal. And the reason that that's helpful is because, as you can tell, the denominator on this second function is then reducible. I actually end up with negative x over x, which means that this is equal to the limit, and if I reduce that, of negative 1. And that's just a constant. So the limit as x approaches infinity of a constant negative 1 is negative 1. So this limit is actually negative 1. All right, we have one more, and this one really looks like it should be giving us a different answer, or that it looks like it's something quite different, simply because we have that sine x involved. But what I want you to consider is I want you to consider what the graph of sine of x looks like. So the graph of sine of x has this sort of cyclic behavior, and it looks like this, roughly anyway. And it tops out, or it peaks every time at the value 1, and it has a valley every time at the value negative 1, which means it oscillates, or it goes up and down, it bounces up and down between positive and negative 1. So why does that matter? Well, it matters because this sine feature right here then doesn't actually have a limit, right? As it goes to positive infinity, it keeps bouncing up and down between positive and negative 1. So if you think about it, one of the things we worked at in the last section, section 3, I believe it was, so a couple sections ago, is we talked about being able to rewrite this limit in such a way that we could sort of, well, in fact, let me just make one more comment before I get there. We could actually ignore the plus 4 on the bottom just like we did before, right? It actually doesn't affect anything as x goes to infinity. So what we actually see happening here is that this x squareds can cancel. So this actually leads us into having the limit as x goes to infinity of 2 sine of x, which is actually a lot easier to sort of work at and think about. This sine of x now bounces back and forth between positive and negative 2. So this limit actually does not exist. And the reason it doesn't exist is because it's going to have the same sort of a graph as this one, except that it's going to go up and down between 2 and negative 2. So as we go to the right forever, there is never a value that we actually approach, because we keep going up and down and up and down and up and down. Now I know it's not actually in here, but I want you to think about a different function that's very similar to this one. At least on the appearances, it looks like it's going to be similar. We're going to do the same limit as x approaches infinity, but this time I want to write this as 2x over the sine, times the sine of x over the x squared plus 4. Now parts of this are the same. That is to say that the plus 4 still doesn't matter. But parts of it are different as well, right? So this limit as x approaches infinity could reduce if I ignore the plus 4 because it doesn't affect the limit value. This could actually reduce to 2 sine of x over x. Now this is different because on this one we actually have two pieces going on. We actually have a limit where I'm going to write this in a slightly different way to help us to visualize this. The limit of 2 over x times the limit of sine x. Again, as x goes to infinity on both of these. Now the reason that this is helpful is because notice this graph is actually the same thing as this theorem we saw over here. I know it's got a 2 on top, but again, the 2 doesn't change the limit. The 2, in fact, we could even pull it out in front. Then maybe that would be more helpful to see. I should actually write this 2 in front here, and then this is 1 over x. So the part that's circled down in green actually is a limit of 0. So I know this is terrible notation for me to do this, but I'm going to go up here for a little bit. So this is actually 2 times the number 0. And then this piece does not have a limit, but it does bounce up and down between 1 and negative 1. So this is going up and down between 1 and negative 1. But notice that means we're multiplying 2 times 0 times some number between negative 1 and positive 1. I don't care what it is. This is a very interesting one. This actually becomes 0. And let me show you just briefly what the graph would look like if we looked at this one. Now, this is not by any means exact, but I want to give you a visual, and you can graph this in your calculator to get a better visual. But what is visually going on is that it's going up and down, but it's getting closer and closer as it goes up and down to the x-axis. Now, it's not actually an asymptote the way we've sort of thought about the asymptotes for the other functions. That is to say, it actually hits that line y equals 0 or the x-axis lots of times. But notice what you're really kind of got going on here. If I had drawn it well, and I of course I didn't, that's not too bad. This is tapering off and it sort of looks like a megaphone or something going on. Now this sort of, the way I drew it, gave you the illusion that it stops oscillating. It doesn't stop oscillating, but it does get so very tight around that x-axis that is the limiting behavior. It is approaching that x-axis, which means this limit, as x approaches infinity, again, let me call it f of x in this case, is still going to be 0. Yes, does it bounce up and down? Absolutely. But the bouncing up and down gets tighter and tighter and tighter around the x-axis, which is the y value 0.